Welcome, Calculus 3 students. We're talking about partial derivatives today. So let's say here I am right there sitting in this little valley here, and you say, well, what's the slope of the land like? And I say, well, that depends on which way I'm getting ready to go. What a partial derivative is I hold one variable constant and just tell you what the slope of the line is, say in one direction. So I could tell you what the slope of the line was in the north-south direction or the east-west direction, but I don't try to tell you what it is in all directions. I'm just looking at it in terms of either just the x or just the y. So note, the partial derivative of f with respect to x, I'm going to hold the b value constant. Notice how the b value is constant here, and the a is what I'm looking at getting closer and closer to, taking that limit as h approaches 0. And then the partial derivative of f with respect to y, notice that I hold the a value constant. So let's do the partial derivative of f with respect to x. And that means I'm going to hold the y value as a constant. So partial derivative of this with respect to x is a 2x. Partial derivative of y, if he's held as a constant, that's just going to be a 0, and then that, of course, with the 4, it's going to be a 0. Now, this next question asks me to compute this partial derivative of f at that particular point. So how I'll write this is partial derivative with respect to x at the point 2, -4 is going to be 2 times that 2, and this answer would then be 4. Now I need the partial derivative of f with respect to y. This would be -2y. The x squared and the 4 are held constant. Now the evaluated at the point 2, -4, this answer would be -2 times the -4. This answer is then 8. Let's look at the partial derivative of a function such as sine of xy. Alright, so I'm going to first I'll do the partial derivative of f with respect to x, then I'll do the partial derivative with respect to y. So let's look at this, the partial derivative of f with respect to x. Take the derivative of the outside function, that would be cosine, leave the inside alone, times the derivative of the inside. The derivative of the inside involves the product rule. That means I would take the derivative of x, which is a 1, times y, add to that, leave the x alone, take the derivative of y, but that is a constant, so that would be 0, and this will then be y cosine xy. And I'm going to also do, let me scroll this up just a little bit, the partial derivative of f with respect to y, and with this I'll do the same thing again. I'll take the derivative of the outside, leave the inside alone, times the derivative of the inside. Derivative of the inside, if I take the derivative of x, that's a 0, so then I would, doesn't matter what happens to that, then I'd say plus, take the derivative of y, that's a 1, so this would be an x, and this partial derivative is x cosine xy. I'm going to play over here. The partial derivative of g with respect to x is going to be, I'll need the product rule here, so that's going to be 2x, leave the other guy alone, plus x squared times the derivative of this e to the xy. Derivative of e to the xy is going to be the e to the xy times the derivative of the x times y, which would then be the product rule. The product rule would say be y plus, because derivative of x is 1, and then that would be a 0. I'm going to clean this up a little bit. Alright, that looks a little prettier to me. Partial of g with respect to y. Once again, I have the product rule, but that x squared part is going to drop, so then it's just going to be x squared times the derivative of this e to the xy with respect to y, so that'd be e to the xy, then times the derivative of x times y, which would then be x. So I'm going to get x cubed e to the xy for this one. And that was fun, wasn't it? Now, just with regular derivatives where we can take the second and the third derivative, we can also take the second and the third and the fourth partial derivative. We can carry on from there. But we have the instance where we're going to do the partial derivative of f with respect to x, and we have the partial derivative of f with respect to y, and then we'll once we get that answer, then we can take the second derivative, but we'll have to be able to go on that with respect to x and with respect to y. So I'll go ahead and get this one done first. Just walking through that one and taking the derivative with respect to the particular variable. Now what I'm going to do is I'm going to take the derivative of f, but it's going to be the second derivative, and this will be with respect to x on the second. But then I can also do the partial second derivative of f with respect to x and then respect to y. And notice that the order of this is going to make a difference. I could do second partial derivative of f with respect to y, then x. So this does make a difference in your ordering. So be very careful with your notation here, because how you write this makes a difference. And so this one's going to be with respect to y, then with respect to x. And we'll go look at those. Okay, just doing the first set. I just took the derivative of this with respect to x, and then I took the derivative of that with respect to y. I'll do the same thing again here. I'll take the derivative of this with respect to y. Looks like I'm just going to get 30xy here with respect to x. It's going to be 12x cubed minus 2 plus 15y squared. And let's look at these two guys right here and note that in this case they are exactly the same thing. From that we now get a theorem which tells us that all I need to be sure to be careful of my ordering. In the long run, the order doesn't matter. And then that is very interesting to note. And of course that theorem is proven in the text. In our next problem, we're going to take the partial derivative of this with respect to x. Alright, so if we take the partial derivative of this with respect to x, that means I'm going to get this e to the negative xy thing. And then I'm going to take the derivative of that negative xy, and that's going to give me a negative y. And I'm to leave this other guy alone because I was using the product rule, cosine z. Cleaning this up just a little bit, I'm just write minus y e to the minus xy cosine z. This next one, I'm going to take the derivative of this function with respect to y. Once again, it's the product rule. So I'll have this e to the minus xy times the derivative of this minus xy, which in this case is going to be minus x. And then leave the second one alone. And then, of course, it is the product rule, but the derivative of that constant, because it is a constant with the partial, is just going to be 0. So I'm neglecting to do that, but I actually did. I just didn't write it down. In the next one, I once again use the product rule. This e to the minus xy is just a constant, and then the derivative of this cosine z is just minus sine z. In example 5, I'm to determine the rate of change of pressure with respect to volume. So for the A part, it's the partial pressure with respect to volume. So I'm going to rewrite this equation as P equals KT over V. And if I do that partial, I will end up with that V is in the denominator, so it's like V to the minus 1, and when I take that derivative I'm going to end up with minus KT over V squared, because I brought down that negative 1, subtract 1 off of there. What this says is that this is how the pressure changes with volume, and we hold the temperature constant. So it seems as though pressure is going to be a decreasing function of volume. So that means the pressure decreases as the volume gets larger. B, find the rate of change of pressure with respect to temperature. Pressure with respect to temperature. So when I take this derivative, I'm going to end up with just a K over V, and because that T, when I take that derivative, that T drops out of there. So this would mean that pressure is an increasing function of temperature at a constant volume. So let's look at these level curves. Looking at these level curves for different values of pressure, you can see that on this vertical, as P is increasing with a constant volume, P is increasing with increasing temperature. With a constant temperature, P is decreasing with increasing volume, and that is what that level curve is telling us. We have a definition of differentiability to look at. Whether or not something is differentiable does not necessarily mean that just because a partial exists doesn't mean that it's necessarily differentiable. And this last example exemplifies that, because the partials do exist because it was dependent on your direction of approach, just like the concept that we introduce partial derivatives with, where we would talk about the slope, and we can't talk about the slope in all directions, but we would talk about it in just one direction. Now, if both partial derivatives on a function that is dependent on both x and y, if both of those partials exist, then the function is differentiable. But just because we have one partial doesn't mean that it is differentiable. But if it is differentiable, then we know that it is continuous. This function is continuous, but that does not necessarily imply that it is differentiable. And this one is not, because even though it's continuous, because they put in the point for the 0, 0, as you approach the 0 from different directions, you get a different value, which would imply that it is not differentiable. And that concludes section 13.4.